Hello everyone, welcome back. In this particular video, we're going to talk about the reactions of epoxides, but under acidic conditions. Now, the reactions of epoxides under acidic conditions, these are also ring opening reactions. Previously, we've talked about the reactions of epoxides with nucleophiles. Those were reactions under basic conditions, and those involve the ring opening of epoxides. So let's see what happens when epoxide or when an epoxide reacts with an acid. What sort of mechanisms are involved and what sort of products are possible under these conditions. Let's start off by the reaction of an epoxide with an HX, okay? So that's like the simplest scenario that we are considering here. So reaction with HX. So where X is a halogen, chlorine, bromine, iodine, any of those. Okay, so what happens when an epoxide reacts with a hydrogen halide? The product that we get under these conditions is an alcohol again. Okay, the epoxide ring opens up to give us an alcohol, but on the other end there is a halogen, and again, notice how these two functional groups are separated by two carbon atoms. That's because we have the two carbon atoms here. So those two carbon atoms are also there in the product, and the two functional groups are separated by two carbon atoms. So what's the mechanism of this reaction? Now, if you recollect, when we did the reaction under nucleophilic conditions or basic conditions, the first step was the attack by the nucleophile. On the other hand, under acidic conditions, the first step is actually a protonation. Okay, so the epoxide here is going to react with the hydrogen halide. It gets protonated, the oxygen gets protonated, the halogen gets kicked out. So we will get a protonated epoxide here. Positive charge, and plus we have an X minus. And so the first step is the protonation. The second step is the nucleophilic attack. And the nucleophilic attack is again an SN2 attack. And in this particular case, because we're dealing with the symmetrical epoxide ethylene oxide, the halide can go and attack at either of these two carbon atoms. Doesn't matter which one it attacks. So let's say if the halogen goes and attacks this carbon, then the ring is going to open up from that side, and essentially that's going to lead us to the product within the second step. So the second step is the nucleophilic attack. Okay, and that gives us the product. So the order of, or the sequence of events seem to be flipped here. Okay, they are flipped compared to the nucleophilic attack itself, or the attack under basic conditions. In that particular case, the nucleophile attacks first and then the protonation happens. Here, the protonation happens first and then the nucleophile attacks. Now, this is not like a universal mechanism though, when the epoxide is ring opening under acidic conditions. We'll see that in some of the subsequent examples that we look at, we're going to see an extra step happen. So it really depends on what is the reagent and how is the reaction going on, okay? So this was the first case where you reacted an epoxide with a hydrogen halide. Now, let's look at the second example here, where the mechanism is slightly different, okay? So let's say the second one is when the acid, is, or when, not the acid, when the conjugate base of the acid is a weak nucleophile. Okay, so in the previous case, we used the hydrogen halides. where the conjugate base of the acid was the chloride or the bromide or the iodide, those are good nucleophiles. What if we use an acid where the conjugate base of the acid is a weak nucleophile? And this is very typical of how these reactions are done. So an example of an acid like that, okay, is sulfuric acid. Because when you use sulfuric acid, the conjugate base of sulfuric acid is bisulfate. Here, that is the conjugate base of sulfuric acid, and this conjugate base is resonance stabilized. It is resonance stabilized, and hence this is a weak nucleophile. In fact, it's not even a nucleophile. It's a very, very weak nucleophile. Okay, so what if we are dealing with an acid like that? So let's look at an example where the epoxide that we just dealt with, the ethylene oxide, now reacts with sulfuric acid. And this is dilute sulfuric acid. Okay, so this is dilute sulfuric acid, which means it is sulfuric acid plus a lot of water. Okay, and whenever you have this scenario, you can pretty much treat it as a hydronium ion. Okay, that's what you're dealing with here. If you have dilute sulfuric acid, then you are in aqueous conditions. Under aqueous conditions, then you have sulfuric acid plus water. And so you're dealing with a hydronium ion in some sense. When we do this reaction, the product that you get is ethylene glycol. Okay, ethylene glycol, that is the product. But the mechanism is slightly different. There's an additional step from what we've seen previously. Okay, so what happens here is, since we're dealing with the hydronium ion, sulfuric acid plus water here, the first step is still the same. The epoxide gets protonated. So we can use the hydronium ion here because our conjugate base is not a significant nucleophile here. So we can use that. So essentially the epoxide oxygen gets protonated. So the first step is again a protonation. Okay, so we are doing a protonation here. And that will give us the protonated epoxide as the product, along with water. Okay, along with water. Now, it could be this water molecule. If not, there's a lot of water around because we're dealing with a dilute acid. Okay, so, and again, these are acid-base reactions, so they would be in equilibrium. Now, once you get this protonated epoxide, the water molecule can now act as a nucleophile and it can come and attack. Okay, that's a good enough nucleophile, so it can come and attack and it would ring open. So that means the second step here is the nucleophilic attack. It is a nucleophilic attack, and it is an SN2-like attack here as well. Okay, so the water molecule comes and attacks, the epoxide ring opens up. So what I'll get is an OH on this carbon here, 1 and 2. Okay, so OH is connected to 1, and then we have 2. So this is 1, that's 2. And on 2 now, there's the water molecule. So there's the water molecule connected to carbon number 2 because water attacked carbon number 2. So we get that species. And notice this is not our product, ethylene glycol. It's not a neutral molecule. So whenever you end up with an intermediate like this, there is an additional step, but there is one last step, which is a final acid-base reaction, a proton exchange. Okay, so we can bring in another molecule of water because we are under aqueous conditions. There's a lot of water around. we can bring in another molecule of water, which is going to deprotonate that, and it would give us the ethylene glycol. And as you can see, it's going to generate hydronium ion along with it. So that means the hydronium ion that we used initially is regenerated at the end of this mechanism or this mechanistic cycle. And so we don't really need a lot of acid here. Again, you just need a little bit of acid. So this reaction would be catalytic in acid. Okay, so that's the reaction where you're using an acid with a very weak conjugate base. So the solvent is what basically kicks in and it does the reaction for you. We'll look at another example of this, okay, to basically see how it would operate if we change the system slightly. Okay, so let's look at another example where you're using the same epoxide, and we have sulfuric acid, but now we are in methanol as a solvent. Okay, so sulfuric acid with methanol as a solvent, and there's a catalytic amount of sulfuric acid. That means there's a tiny bit of sulfuric acid. Catalytic amount of sulfuric acid is what we have here. In this particular case, our solvent is methanol. Okay, we have the sulfuric acid, so we can use the sulfuric acid for the mechanism, but it's not required. You can use the sulfuric acid directly for the mechanism. So let's say we use sulfuric acid. I'm going to draw out this bond because we're going to show the mechanism. So I need to have the bond drawn out to show electron push arrows. So the oxygen from the epoxide gets protonated. Electrons go to that oxygen atom. This would give me a protonated epoxide. And along with that, I would have HO minus. That's the conjugate base. Okay, so this was the acid. This is the conjugate base. This is behaving as a base. That's the conjugate acid. So we're still doing an acid-base reaction, a proton exchange. So we get this protonated epoxide, but the conjugate base that we've generated, unlike a halide, this is a very weak nucleophile. So it will not attack this protonated epoxide. Instead, what's going to happen is the solvent here, which is methanol, that will kick in and it would come and attack this epoxide. Again, at this point, there's no bias. They're both equal of equal substitution. They're both primary in nature. So it can attack either one of those carbon atoms. So the epoxide ring opens up. And so what we will get is a hydroxyl, the oxygen with the hydrogen on this carbon, and then two carbons, 1, 2. And on the second carbon is the methanol. So the methanol is now connected to that second carbon, has one lone pair, has a positive charge. And like you notice in the previous example, now we have a species with a positive charge. So whenever we get to that, we're going to do one additional step, which is going to be an acid-base reaction or a proton transfer reaction. So we can bring in another molecule of methanol because that's a solvent. There's a lot of it around, and the methanol can go and deprotonate that hydrogen, or it can deprotonate, do a proton transfer. Electrons go to that oxygen such that in the end, my product is going to be OCH3 plus a hydronium ion. Okay, sorry, not a hydronium ion. In this particular case, it's going to be the methanol protonated methanol molecule. So that would be your side product, and this is your product. Now, if you compare what we are doing here, or at least the products, to what we've seen in the nucleophilic attack, the products are the same, but the reaction operates through a different mechanism, okay, because we are under acidic conditions now. Now, one thing I want to mention here is whenever you have a strong acid like sulfuric acid in a solvent like methanol, there will be an acid-base reaction between sulfuric acid and methanol. So in principle, you're going to get that species, the conjugate acid of methanol. So we could use the conjugate acid of methanol to start off this reaction here. Instead of sulfuric acid here, we could have used that conjugate acid of methanol and done the same mechanism. Okay, so that is an introduction to the ring opening reactions of epoxides under acidic conditions. And we've looked at examples where we have hydrogen halide acids, where the conjugate base of the acid is a good nucleophile. And we looked at examples where the conjugate base of the acid, is a poor nucleophile, and how the reaction proceeds under these conditions. We'll look at other aspects of regiochemistry and stereochemistry in a subsequent video. Bye.